This is the second mini lecture for section 2.1 of the textbook. Now we're going to talk about set relations and operations. When we talk about set relations, we're talking about different ways that sets can be related to each other. When we talk about set operations, we're talking about things you can do to sets to make new sets. So first of all, two sets, A and B, are said to be equal if they contain precisely the same elements. This is written A equals B. So notice that we don't say that A equals B if they're just the same size. Two sets have to be literally the same. For example, if I have a set of 5 students and a set of 5 desks, those are not equal sets because the students are not the desks. Okay, the objects have to literally be the same. It is possible to talk about sets being the same size, but we'll talk about that a little bit in the next section. Okay, right now we're just talking about the sets themselves. Two sets are only equal if they're literally the same objects. So here's an example. Let B be the set of birds, and let F be the set of animals with feathers. Well, every bird is an animal with feathers, and every animal with feathers is a bird. So those are equal sets. They're precisely the same. Okay, so equality of sets is the first relation. Okay, next, if A and B are two sets, then we say that A is a subset of B if every element of A is also an element of B. This is written as A is a subset of B using this little symbol. It looks like a horseshoe with a line under it. Okay, that A is a subset of B. Everything in A belongs to B. So for example, let's let B be the set of birds and let C be the set of chickens. Every chicken is a bird, so C is a subset of B. You could illustrate this with a Venn diagram as follows. Here's our set of chickens, and then containing that, but also potentially other things, we have B, the set of all the birds. So within B, you've got the chickens, but this little region here, that would correspond to the birds that are not chickens. Now let's think about this simple picture for a minute. Yeah, we know that there are lots of birds that are not chickens. You know, there are things like grackles and turkeys and who knows what. So what would happen if all the birds in the world suddenly died, except for the chickens? What would happen to the set of birds? Well, yeah, this picture would still be meaningful. You could still draw this picture. It would just be that there would be no birds in this region. There would be no birds that are not chickens. Every bird would be a chicken. Now, what would that mean for the relationship between these two sets? Well, in that case, not only is every chicken a bird, we could also say that every bird is a chicken, because we just lost every other bird. So if that were to happen, and hopefully it doesn't, but if it did, then these two sets would end up being equal. So that the picture wouldn't really be incorrect. It's just that there wouldn't be any birds in this region. There are no birds that are not chickens. So when I say that C is a subset of B, I'm allowing for the possibility that they're actually equal. I would like to be able to describe a situation in which I know that C is definitely smaller. In other words, it leaves some things out. You know, there are some birds that are not chickens. And if I know that about C, then I can call it what we refer to as a proper subset. So again, the definition of subset allows the two sets to be equal. If A and B are two sets, then A is a proper subset of B. If A is a subset of B, then A is not equal to B. So this is written as A is a proper subset of B. in order for A to be a proper subset of B, it has to be smaller than B, in the sense that it leaves some things out. So for example, if I'm talking about my chickens and birds, every chicken is a bird, but not every bird is a chicken. So C is a proper subset of B. So it's true to say that C is a subset with a line under it, but it's also true to say that it's a proper subset. Now let's think about our feathered animals. Okay, F was the set of animals with feathers. Now every animal with feathers is a bird, so I can certainly say that F is a subset of B. However, every bird has feathers. So in fact, F is equal to B. So it is true to say that F is a subset of B because every feathered animal is a bird. But there are no other birds. Every bird has feathers. So these are actually equal sets. So it is not true that F is a proper subset of B, because they're actually the same. Okay, the notation is set up to make you think of less than or equal to and less than. Subset is like less than or equal to. Proper subset is like less than. So, when I say that C is a subset of B, I'm saying not only is C contained inside of B, but it's actually smaller. Okay, when I say that F is a subset of B, which I can certainly do, I'm just saying that F is contained inside of B. I'm not necessarily saying that F is smaller than B, and in this case it's not. But it's also true to say that C is a subset of B. So these are all true statements. The one that would not be true is to say that F is a proper subset of B. That's the one that would be false. Okay, so we begin to talk about our sets operations. Before we do that, let's talk about the empty set. The empty set is the set that has no elements at all. And it might seem like that's kind of ridiculous to define a set that just has nothing in it. We'll see that it's very useful. It's useful for a lot of reasons. For one thing, if I talk about something like, what is the set of flying elephants? Well, there are no flying elephants. But what I described is a set that's well defined. So I would still like to be able to refer to that as a set. I don't want to have to say, well, that's not actually a set because there are no flying elements. No, it is a set. It's the empty set. And sometimes, usually you see the empty set written as a circle with a slash through it. Remember, don't ever use that symbol for zero. That's kind of out of date and it's confusing nowadays. Just use a circle for zero. Circle with a slash is the empty set. That means the set with nothing in it. And sometimes in some books, though not in our book, you see that written as just a pair of braces with nothing in between them. And that's to underscore the fact that this is just a set with nothing in it. Okay, so let's talk about the first of our operations. Okay, this is the complement of a set. If A belongs to a universe U, then its complement is the set A with a bar over it of all elements in U that do not belong to A. Okay, so it's the set of everything in U that is not in A. You can draw it as a Venn diagram as follows. So, here's our universe U. Here's our set A. The complement is everything outside of it, everything that's in that universe that is not an A. Okay, so the word complement, it kind of means opposite, but it means it in such a way that when you put them together, you get the whole. Like when you talk about a married couple complementing one another well, you mean that each of them has strengths and weaknesses, but the strengths of one make up for the weaknesses of the other, so that when you put them together, then you get a good whole. Okay, that's the way we're using the word complement here. Note that it's a complement with an E. A compliment with an I would be something nice that you say about somebody, which is not what we're trying to do here. All right, so let's talk about our universe in sets A and B above, the lists of numbers. So remember that A was the set of odd numbers in U. So that means that the complement of A would be the set of even numbers in U. So it'd be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. And the complement of B, that's everything that's not in B. B was the set of multiples of 3. So the complement is the set of elements of U that are not multiples of 3. So 1, 2, 4, 5, 7, 8, 10, 11, 13, 14, 16, 17, 19, 20, 22, 23, and 25.